Have you ever looked up at the night sky and felt like there's something more, something just beyond our understanding, silently shaping the universe? What if I told you that everything we see, from the tiniest particle to the vast expanse of galaxies, might be influenced by invisible forces, hidden fields woven into the fabric of reality itself? These aren't the stuff of science fiction. They're real, or at least, they're some of the most compelling theories in modern physics. Hidden fields, elusive, mysterious, and utterly fascinating, could be the unseen architects of the cosmos, dictating the rules of existence in ways we're only beginning to unravel. Think about the last time you held a magnet. You couldn't see the force pulling it toward metal, but you knew it was there. Now, imagine that same invisible influence, but on a cosmic scale, fields so profound they might explain dark energy, the expansion of the universe, or even the very nature of time. Scientists call these hidden fields, and while they've never been directly observed, their fingerprints are everywhere. From the way particles behave in quantum experiments to the strange, unexplained motions of distant galaxies, these fields could be the missing piece in our puzzle of reality. It's like the universe is whispering secrets to us, and we're just starting to listen. This is where things get truly mind-bending. What if these hidden fields aren't just passive backdrops but active players, shaping the destiny of everything? Some theories suggest they could be responsible for the birth of universes, the laws of physics, or even the illusion of time itself. Others propose that we might one day harness them, unlocking technologies beyond our wildest dreams. But here's the catch: the more we learn, the more questions we uncover. That's the beauty of it. This isn't just a story about science, it's a journey into the unknown, a chance to explore the deepest mysteries of existence. And today, we're diving into 30 of the most astonishing theories about these hidden fields, each one more incredible than the last. So, are you ready to step into the shadows of the universe and discover what might be lurking just out of sight? Let's begin. You might think of empty space as just that, empty, but quantum physics tells a different story. Even in a perfect vacuum where not a single particle exists, the universe is far from still. Tiny bursts of energy flicker in and out of existence so fast they're almost impossible to detect. Scientists call these quantum fluctuations, and they're not just theoretical, they've been measured in labs. Picture a calm ocean at night. From a distance it seems perfectly still, but up close you'd notice ripples and tiny waves constantly forming and dissolving. That's what's happening in so-called empty space, except instead of water, it's energy itself bubbling beneath the surface. Now here's where it gets wild. These fluctuations might not just be random noise, they could be the signature of hidden energy fields woven into the fabric of reality. Think of them like invisible currents beneath the ocean, shaping everything that moves through them. In quantum experiments, particles pop into existence where they shouldn't, or vanish unpredictably. Some physicists believe these strange behaviors are clues, traces left behind by fields we can't yet see. And if that's true, these fields could be doing much more than just making particles dance. They might be the engine behind dark energy, the mysterious force accelerating the expansion of the universe. Imagine blowing up a balloon with tiny dots drawn on it. As the balloon expands, the dots move apart. Now think of those dots as galaxies, the balloon itself. That's space itself stretching, and those quantum fluctuations could be the force making it inflate faster and faster. Some theories even suggest these hidden fields are what created the universe in the first place, sparking the Big Bang with their unstable, seething energy. It's a humbling thought that what we call nothingness might actually be the most active, creative force in existence, shaping the cosmos from the shadows. So the next time you look up at the night sky, remember, even in the emptiest void, there's a hidden storm of energy, unseen and untouchable, yet possibly holding the keys to the greatest mysteries of the universe. And we're just beginning to understand its language. most of us have heard of the Higgs field, the invisible cosmic molasses that gives particles their mass. But what if it's not alone? What if there are other, even stranger fields hiding in plain sight, shaping the universe in ways we're only beginning to guess? The Higgs was just the first domino to fall. Scientists now suspect entire families of undiscovered fields might be lurking beyond it, each with its own cosmic role to play. Take mass, for example. The Higgs field explains why some particles are heavy while others zip around almost weightless. Picture a crowded party where certain guests move easily through the room while others get stuck in conversations. The Higgs is like the social glue that slows them down, giving them mass. But here's the twist. There might be other parties happening at the same time, hosted by different fields. Some theorists propose that dark matter, the mysterious substance making up most of the universe's mass, could be the guest of honor at one of these hidden gatherings, interacting only through its own secret field. Then there's inflation, the universe's explosive growth spurt right after the Big Bang. For decades, physicists have struggled to explain what could have powered such a rapid expansion. The leading idea, another scalar field distinct from the Higgs that briefly dominated the cosmos. Imagine blowing up a balloon not with air, but with pure energy, a field so intense it stretched space itself faster than light. And just like that, it vanished, leaving behind only the echoes we see in the cosmic microwave background. But the wildest part, these extra fields might not just be relics of the past. Some could still be active today, subtly tweaking the laws of physics in different corners of the universe. Imagine if gravity were slightly stronger in some galaxies than others, or if dark energy changed over time. These anomalies could be fingerprints of hidden fields at work. It's like realizing the rules of the game aren't set in stone, but written in invisible ink, shifting where we can't see. So while the Higgs field was a monumental discovery, it might be just the first page of a much weirder story. The universe could be teeming with undiscovered fields, each whispering its own influence into the fabric of reality. And if we learn to listen, we might finally understand why the cosmos behaves in ways that still leave even the brightest minds baffled. What if dark energy isn't the unchanging force we've assumed it to be? For decades, scientists thought of it as a static background, a cosmic constant gently pushing the universe apart. But what if it's more like a living thing, ebbing and flowing over time? Enter quintessence, the idea that dark energy could be a dynamic scalar field, one that evolves and interacts in ways we're only beginning to theorize. Picture a river that sometimes flows calmly and other times rushes violently. That's the essence of quintessence, a field whose strength waxes and wanes, shaping the universe in unpredictable ways. Unlike the steady push of a cosmological constant, this field might have phases where it accelerates expansion, then suddenly weakens or even reverses direction entirely. Some models suggest it could have been dormant for billions of years before awakening to drive galaxies apart. Others propose it might eventually fade, leaving gravity to pull everything back together in a big crunch. Here's where it gets even stranger. If dark energy is truly dynamic, its fluctuations could leave fingerprints in the cosmos. Variations in its strength might explain why distant supernovae appear dimmer than expected, or why galaxy clusters seem to move in peculiar patterns. It's like finding subtle cracks in a mirror, hints that the force behind expansion isn't as uniform as we thought. Some researchers even speculate that quintessence could interact with other fields, creating bizarre side effects like sudden changes in fundamental constants. Imagine if the speed of light or the strength of gravity shifted over time, all because of this hidden actor behind the scenes, but the most unsettling possibility. This field might not just alter the universe's fate, it could rewrite its own rules. Unlike the Higgs field, which settled into its current state early in cosmic history, quintessence could still be searching for equilibrium. Think of it as a pendulum that hasn't stopped swinging, its oscillations potentially leading to phases of runaway expansion or collapse. One day, it might even trigger a new inflationary epoch, birthing pocket universes with entirely different physics. The beauty of this theory lies in its flexibility. It offers answers where constants fail. Why does dark energy's density seem finely tuned to allow life? Maybe it wasn't fine-tuned at all, but naturally evolved to this state. Could the universe's acceleration be a temporary phase? Quintessence leaves that door wide open. For all we know, the fate of everything might hinge on a field we can't see, changing in ways we can't yet predict. And that's what makes it one of the most thrilling and humbling ideas in modern cosmology. What if the answer to dark matter has been hiding in one of the most delicate, ghostly particles ever imagined? Enter Axion's hypothetical particles so lightweight and shy that they'd make a neutrino look like a social butterfly. Born from a hidden field theorized to explain quirks in quantum physics, Axions might be the universe's ultimate wallflowers, barely interacting with anything yet collectively shaping the cosmos on a grand scale. Picture a vast, invisible ocean where every drop is an action. Billions could be passing through you right now, leaving no trace, no deflection, no collision, just a faint whisper of their presence. Unlike the heavy, lumbering particles once thought to make up dark matter, Axions would be feather-light, zipping through space effortlessly. But here's the genius of the idea: their sheer numbers could add up. Think of a single snowflake, almost weightless, but trillions upon trillions of them. Suddenly, you've got an avalanche. Axions could be the same, their combined gravity sculpting galaxies into the structures we observe today. The origins of this theory are as fascinating as the particle itself. Axions weren't invented to solve dark matter. They emerged from a puzzle in quantum chromodynamics, the theory governing how quarks stick together. Physicists realized that unless nature had an almost perfect symmetry, the equations predicted bizarre effects like neutrons spinning differently in electric fields. To avoid this, they proposed a new field that would clean up the math. And just like that, the Axion was born, a particle no one expected, solving two mysteries at once. But how do you find something that barely interacts with matter? Scientists have gotten creative. Some experiments use ultra-sensitive magnetic fields in chilled vacuum chambers, hoping an axion might decay into a detectable photon. Others look for axions converting into radio waves near neutron stars, where magnetic fields are intense enough to tease them out of hiding. It's like listening for a pin drop in a hurricane, but researchers are inching closer. Recently, strange signals from distant quasars and unexpected light distortions in lab experiments have sparked excitement. Could these be the first hints of axions weaving through the cosmic tapestry? What's tantalizing is how axions could rewrite the rules. If they exist, they'd prove that dark matter isn't just one thing. It might be a mix of different actors, each playing their part. Imagine a universe where dark matter includes both massive particles and these ethereal axions, each sculpting galaxies in their own way. Some theories even suggest axions could form bizarre, wave-like structures, creating ripples in spacetime itself. So while we haven't caught one yet, the hunt for axions is more than a scientific quest. It's a test of whether the universe's hidden fields are even stranger than we dreamed. And if we succeed, we might finally lift the veil on the invisible hand guiding the stars. Imagine a cosmic shapeshifter, a force so elusive that it alters its very nature depending on where you look. That's the essence of chameleon fields, hidden players in the universe that adjust their behavior to blend into their surroundings, escaping detection in our labs while potentially driving the expansion of the cosmos itself. Unlike static fields like the Higgs, these are masters of disguise, appearing weak in dense environments like Earth but growing dominant in the vast emptiness of space. The genius of this theory lies in its elegance. Picture a chameleon changing color to match its background. Only here, it's not about camouflage but survival. In regions packed with matter, like our planet, the field suppresses its effects, becoming virtually undetectable. but in the near-perfect vacuum between galaxies, it stretches its influence, pushing space apart. This could explain why dark energy seems so uniform across the universe yet vanishes under close scrutiny. It's not that the force isn't there, it's hiding in plain sight, recalibrating itself based on the density of its surroundings. Scientists first proposed chameleon fields to solve a glaring puzzle. Why haven't we detected dark energy directly if it's everywhere? Traditional models suggested it should leave subtle traces in particle experiments, yet decades of searching turned up empty. But if dark energy isn't a constant force but a dynamic field that feels its environment, everything clicks. Near Earth, surrounded by matter, the field dampens its strength, evading our instruments. Venture into deep space and it sheds its restraint, unleashing enough power to accelerate galaxies apart. Testing this idea isn't easy, but researchers have devised clever workarounds. One approach involves ultra-sensitive torsion balances devices that measure infinitesimal twists caused by unseen forces. By isolating these instruments in vacuum chambers, scientists hope to catch the field off guard, revealing its presence as it weakens in low-density conditions. Another method looks for subtle anomalies in planetary orbits. If the chameleon field's strength varies even slightly across the solar system, it could nudge planets in ways gravity alone can't explain. What's truly mind-bending is how this theory bridges scales. On cosmic levels, chameleon fields could dictate the fate of the universe, while locally, they're ghosts slipping through our fingers. Some models even suggest these fields might interact with dark matter, creating feedback loops that amplify their effects over time. Imagine a dance where one partner adjusts their steps based on the music only here. The music is the density of the universe, and the dancers are forces shaping reality itself. For now, chameleon fields remain theoretical, but their potential is staggering. If proven real, they'd revolutionize our understanding of dark energy, proving it's not a monolithic constant but a living, adapting entity. More than that, they'd hint at a universe far more responsive and nuanced than we ever imagined, where even the laws of physics might bend to their surroundings. And that's a revelation worth chasing. The universe wasn't always this vast, orderly expanse we see today. In its earliest moments, it was smaller than a single atom, and then, in a fraction of a second, it exploded outward faster than the speed of light. What could possibly power such an extreme transformation? The leading suspect is something called the inflaton field, a hidden force so powerful it didn't just shape the cosmos, it birthed everything in it. Think of the inflaton field as a cosmic pressure cooker. Picture a pot of water on the stove, heating up until it reaches a rolling boil. The inflaton field was like that boiling point, a state of unstable energy desperately seeking equilibrium. But instead of steam, this field released something far more spectacular, space-time itself stretching exponentially in an event called cosmic inflation. For a fleeting moment, this field dominated the universe, pushing every point in space apart at an unimaginable rate. Then, just as suddenly as it began, the inflaton field collapsed, its energy decaying into the particles and radiation that would eventually form stars, planets, and us. The beauty of this theory lies in the clues it explains. Without inflation, the universe wouldn't look the way it does. Why is the cosmic microwave background, the afterglow of the Big Bang, so eerily uniform across the sky? Inflation stretched tiny quantum fluctuations into vast, smooth patterns, ironing out irregularities like a cosmic steamroller, and those same fluctuations. They became the seeds for galaxies, tiny ripples magnified into the cosmic web we see today. It's as if the inflaton field left a blueprint etched into the fabric of reality itself. But here's the twist: the inflaton field didn't just vanish. Its decay might have been the spark that ignited the hot, dense plasma of the early universe. Imagine a snow globe shaken violently when the inflaton field finally settled. It released all that pent-up energy, filling the cosmos with light and matter. Some theories even suggest remnants of this field could still exist today, lurking in the form of ultralight particles or faint energy waves, subtly influencing the universe's expansion. The wildest part, we might be able to test this. If inflation happened, it would have sent gravitational ripples, primordial waves crashing through spacetime. Experiments like the Bicep telescope hunt for these echoes in the cosmic microwave background, searching for faint swirls that could confirm the inflaton field's dramatic role. Others look for indirect signs in particle colliders, hoping to recreate slivers of the energy conditions that existed back then. What's astonishing is how one theoretical field could answer so many cosmic riddles. From the universe's sheer size to its perplexing smoothness, the inflaton field offers a framework that feels almost too elegant to ignore. And if we're right, it means everything we see, every galaxy, every atom, is just the aftermath of a hidden force's fleeting, universe-altering tantrum. A force so powerful it forged reality in less time than it takes to blink. Now that's a creator worth knowing. What if the hidden fields shaping our universe aren't just invisible? What if they're operating in dimensions we can't even perceive? This is where string theory throws open the doors to a wild possibility, that our reality is just a thin slice of a far richer cosmos, with forces and fields spilling into extra dimensions we're blind to. Imagine living in a painting, unaware of the gallery around you. That's us trapped in our familiar four dimensions, while gravity, dark matter, or even entirely unknown forces might be leaking into our world from higher dimensional spaces physicists call the bulk. At the heart of this idea are brain's membranes of reality floating in a higher dimensional expanse. Picture a soap bubble drifting in the air, its surface a self-contained universe. Now imagine other bubbles nearby, each with their own physics, occasionally brushing against ours. The fields permeating these higher dimensions wouldn't just be hidden, they'd be fundamentally unreachable, their influence seeping into our world like echoes through a wall. Some theories suggest gravity feels unnaturally weak because it's not confined to our brain. It's diluted across dimensions we can't access. But here's the twist, these bulk fields might not just be passive bystanders. They could actively reshape our laws of physics. If a higher dimensional field fluctuates, it might suddenly alter gravity's strength in our universe or create phantom particles that appear and vanish inexplicably. It's like living in a house where the walls keep changing thickness, oblivious to the construction happening in a parallel attic. Scientists even speculate that dark energy could be the pressure of our brains straining against these hidden dimensions, a cosmic tug of war stretching space itself. The most tantalizing clue, tiny discrepancies in quantum behavior. Particles entangled across distances, a phenomenon Einstein called spooky action at a distance, might actually be linked through shortcuts in higher dimensions. Think of ants on a sheet of paper, mystified when a fellow ant disappears from one spot and reappears instantly on the other side. To them, it's magic. To us, just a fold in the paper. If hidden bulk fields exist, they could be mediating these bizarre quantum connections behind the scenes. Proving any of this isn't easy, but physicists have ingenious plans. Particle colliders might one day create micro-black holes, not the apocalyptic kind, but fleeting ones that evaporate instantly. Their lifespans could reveal whether gravity is truly leaking into extra dimensions. Other experiments hunt for gravity-like forces that deviate ever so slightly from Newton's predictions at microscopic scales, a potential fingerprint of higher dimensional fields tugging at our reality. So while we're stuck in four dimensions for now, the math hints at a grander stage, one where hidden fields don't just influence our universe but transcend it entirely. And if we're right, the forces we think we know might just be shadows of something far stranger, playing out in realms we can't yet see. Imagine if gravity, the force that anchors us to Earth and shapes the cosmos, could be shaken hands with the other fundamental forces. That's the dream of supersymmetry, a theory so elegant it promises to unite all of nature's forces under one mathematical roof. And at the heart of this grand unification sits the gravitino, a hypothetical particle that could be the missing link between gravity and the quantum world. Here's the catch: gravity has always been the odd one out. While electromagnetism and the nuclear forces play by the rules of quantum mechanics, gravity stubbornly resists, described perfectly by Einstein's general relativity, but clashing violently with quantum theory at tiny scales. Supersymmetry offers a way out. It predicts that every known particle has a hidden superpartner, a heavier shadow version of itself. For gravity, that superpartner is the gravitino, a particle so bizarre it carries the quantum imprint of gravity itself. Think of it as gravity's understudy, stepping in when the usual rules break down near black holes or in the universe's first moments. But the gravitino isn't just a particle, it's the offspring of a hidden field called the supergravity field. Picture this field as an invisible conductor orchestrating how gravity talks to other forces. Where the Higgs field gives particles mass, the supergravity field could govern how gravity meshes with quantum behavior. Some models suggest this field was hyperactive in the early universe, smoothing out spacetime's wrinkles and leaving behind the ultra-uniform cosmos we see today. Other theories propose it's still at work, subtly tweaking how galaxies rotate or how black holes merge in ways that defy standard predictions. Here's where it gets wild. If gravitinos exist, they might not just unify physics, they could be dark matter itself. Unlike typical particles, gravitinos would interact almost exclusively through gravity, making them nearly impossible to detect except by their cosmic footprint. Imagine an army of invisible dancers, their collective weight bending galaxies into shape without ever touching ordinary matter. Experiments like the Large Hadron Collider are hunting for hints, smashing particles at unprecedented energies, hoping to spot a gravitino's fleeting influence. The stakes couldn't be higher. Prove the supergravity field exists, and suddenly the most stubborn puzzles from quantum gravity to dark matter might click into place. It would mean the universe isn't just held together by chance, but by an exquisite symmetry hidden in plain sight. A symmetry where every force, every particle has a mirror. And at the center of it all, a ghostly field whispering gravity's deepest secrets to the quantum world. Einstein's general relativity gave us a universe where gravity is the curvature of spacetime, a smooth, geometric warping that guides planets and bends light. But what if spacetime isn't just bending? What if it's twisting too? That's the radical idea behind torsion fields, hidden geometric properties that could be woven into the fabric of reality itself. Picture a coiled spring alongside a stretched rubber sheet. General relativity gives us the sheet, but torsion adds the spiral, an unseen twist that might explain everything from galaxy rotation to dark matter's grip. Torsion isn't just a wild guess, it's math with pedigree. Early in the 20th century, mathematicians like Eli Cartan realized that spacetime could carry not just curvature, but also microscopic twists at every point. Think of it like a screw's threads, a subtle rotation embedded in the structure of space. Unlike gravity's gentle slopes, torsion would create localized vortices, tiny whirlpools in the geometry of reality. At first, these twists were dismissed as mathematical curiosities, but today, some physicists argue they could be the missing piece in our cosmic puzzle. One tantalizing possibility: torsion might mimic dark matter's effects without needing invisible particles. In galaxies, stars orbit so fast that visible matter shouldn't hold them together, yet something does. If spacetime itself twists near massive objects, those torsion fields could generate extra gravitational pull, tricking us into inferring dark matter's presence. Imagine stirring honey with a spoon. The swirling liquid creates drag that isn't part of the honey itself. Torsion could be spacetime's version of that drag, an emergent force we've misread as missing mass. But the implications go deeper. If torsion exists, it might rewrite black holes. general relativity predicts singularities, points of infinite density where physics breaks down. But torsion could prevent that. Some models suggest twisted spacetime acts like a cosmic shock absorber, keeping black hole interiors from collapsing into mathematical nonsense. Instead of a singularity, you'd get a whirling vortex of spacetime, a torsion core where gravity and quantum effects finally shake hands. It's like replacing a black hole's dead end with a revolving door, one that might even lead elsewhere. Testing this isn't easy, but clues might lurk in neutron stars. These ultra-dense corpses of dead stars spin furiously, warping spacetime around them. If torsion is real, their rotation should imprint faint distortions on passing light, subtle spirals in the starlight that telescopes could catch. Other experiments probe microgravity, looking for anomalies in how objects twist as they fall. Even a whisper of torsion would ripple through physics, offering a backdoor to unify Einstein's gravity with quantum mechanics. The beauty of torsion is its audacity. It takes a century-old idea and flips it sideways, suggesting that spacetime isn't just a stage but an active participant, twisting and responding in ways we're only beginning to map. And if we're right, the universe just got a lot more dynamic, a place where geometry doesn't just bend but dances. What if the Big Bang wasn't a beginning, just the latest chapter in an endless cycle of cosmic rebirth? That's the spine-tingling promise of the ekpyrotic universe, a theory where hidden fields don't just shape reality, they destroy and recreate it over and over. Picture this: our universe isn't floating alone in higher dimensions. It's one of many membranes or brains drifting through an unseen expanse. And when these brains collide, the energy unleashed doesn't just spark stars, it resets the cosmos entirely. At the heart of this idea lies the ekpyrotic field, a hidden force that builds tension between brains like a coiled spring. As the brains draw near, this field stretches tighter, storing unimaginable energy until, bang, they smash together. The impact wouldn't look like an explosion, though. It would be a hyperdimensional implosion, converting that pent-up energy into heat, particles, and space itself. What we call the Big Bang might just be the aftershock of two worlds colliding in a dimension we can't see. The beauty of this model is how neatly it solves cosmic puzzles. Why does the universe appear so uniform, with nearly identical temperatures in opposite directions? Inflation explains this by stretching space rapidly, but the ekpyrotic field offers a wilder answer. Those regions were once part of the same brain, smoothed by eons of slow, pre-collision tension. Imagine two sheets of sandpaper rubbing together. Their surfaces wear smooth before they ever touch. The ekpyrotic field does the same to spacetime, ironing out wrinkles long before the collision that creates a new universe. Here's where it gets even stranger. Unlike the single explosive birth of the Big Bang, the ekpyrotic model suggests cycles. After the collision, the brains rebound, drifting apart until the hidden field pulls them back for another crash. Each collision births a new universe. Each expansion sows the seeds of the next collision. It's cosmic déjà vu on the grandest scale, a loop where every ending is a beginning, and the laws of physics themselves might reset with each iteration. Critics raise fair questions. If this is true, where's the evidence? Supporters point to subtle patterns in the cosmic microwave background, hints of anisotropic bruising from a directional collision. Others hunt for gravitational wave signatures that would carry echoes of brains smashing together. And if the cycles are real, they'd rewrite our destiny. No heat death, no endless expansion, just an infinite rhythm of creation and destruction, with our universe as one note in an eternal symphony. So the next time you hear about the Big Bang, ponder this: what if it was less a birth and more a reboot? A moment when hidden fields, tangled in dimensions beyond our sight, hit the universe's reset button. And if that's true, the cosmos isn't just expanding, it's waiting for its next collision. What if the hidden fields threading through the universe weren't just shaping reality? What if they were actively unraveling it, enter phantom energy fields, one of the most chilling concepts in cosmology. These aren't your typical cosmic actors. They're outliers with negative kinetic energy, warping the rules so drastically that they could one day shred space-time itself in an event called the Big Rip. Picture a force that doesn't just push galaxies apart, but accelerates their separation so violently that no structure, no star, no atom, not even the fabric of space-time, can hold itself together. Phantom energy works like cosmic anti-gravity on steroids. While dark energy gently stretches the universe, phantom fields would amplify that expansion exponentially over time. Imagine pulling a rubber band slowly at first, then faster and faster until it snaps. Now replace the rubber band with reality. The math behind this is as unsettling as the outcome. Most fields have positive energy, meaning they obey the usual rules of physics. Phantom fields flip that script. Their negative kinetic energy means they don't dilute as the universe expands. Instead, they grow stronger, their density increasing as space stretches. It's like pouring water into a cup that never fills. The more you add, the more the cup expands to demand even more. If such a field exists, its influence would start subtly, but over billions of years, it would reach a tipping point where expansion outmuscles every binding force in nature. First, galaxy clusters would drift apart, their gravitational bonds overtaken. Then individual galaxies would disintegrate, stars flung into the void. Next, planetary systems would unravel, followed by stars and planets themselves, torn apart as the phantom field's acceleration overcomes their gravity. In the final moments, even atoms would be ripped asunder, their nuclei unable to withstand the stretching of spacetime itself. The universe would end not with a whimper, but with a scream, a silent, invisible rending of reality at its most fundamental level. Could this really happen? Observations of distant supernovas suggest dark energy's strength is constant, but phantom energy remains a fringe possibility. Some models propose it might emerge if dark energy evolves unpredictably, crossing a threshold where its equation of state dips below -1. It's like a car rolling downhill. Once it passes a certain slope, there's no braking. The scariest part, if phantom energy exists, we might not know until it's too late. Its early effects would mimic ordinary dark energy, hiding its catastrophic potential until the universe was already past the point of no return. Yet for all its apocalyptic drama, the Big Rip isn't just a doomsday scenario. It's a window into how delicate cosmic balance truly is. The fact that such a field could exist at all hints at how little we understand about the universe's underlying rules. And if nothing else, it's a humbling reminder that the forces shaping our reality might still hold surprises far beyond our wildest or darkest imaginings. We've all played with magnets. They have two poles, north and south, inseparable no matter how many times you break them apart. But what if nature has been hiding something from us? What if single magnetic poles particles with just a north or just a south exist somewhere in the cosmos? These hypothetical beasts are called magnetic monopoles, and their discovery wouldn't just rewrite physics textbooks, it could expose an entire hidden layer of reality, gauge fields we've never seen. Imagine if electricity had only positive charges, no negatives. That's how lopsided our understanding of magnetism has been. Maxwell's equations, the bedrock of electromagnetism, work perfectly without monopoles, but they'd work even more beautifully with them. The symmetry would be perfect. Electric charges come in positives and negatives, so why shouldn't magnetic ones? Some theories suggest they're out there, relics from the universe's first moments, when physics operated under rules far stranger than today's. Here's where it gets mind-bending. Monopoles wouldn't just be curiosities, they'd be smoking guns for hidden gauge fields, structures that govern how forces interact at the quantum level. Think of these fields as invisible conductors orchestrating the dance of particles. The electromagnetic field we know is one example, but monopoles could hint at others, fields so subtle they only reveal themselves through rare, extreme events. If a monopole passed through a particle detector, its trail would betray the fingerprints of these hidden fields, warping space around it in ways ordinary magnetism can't explain. The hunt for monopoles has taken physicists from the depths of old moon rocks to the guts of particle colliders. One audacious experiment even strung kilometers of superconducting wire through an abandoned mine, hoping to catch a monopole's passage by the sudden jump in current it would induce. So far, no luck, but theories like grand unification, which aim to merge all fundamental forces, predict monopoles should exist. Their absence is so puzzling it spawned cosmic inflation theory, which suggests the early universe expanded so rapidly that monopoles were diluted to near non-existence. Yet even one monopole sighting could revolutionize physics. It might prove that electromagnetism is just the visible tip of a deeper, richer force structure, one where hidden gauge fields flicker in and out of existence, shaping reality from behind the scene. Some models even suggest monopoles could catalyze proton decay, transforming ordinary matter into pure energy under the right conditions. Picture a particle that doesn't just obey nature's rules but actively reshapes them, a cosmic key unlocking doors we didn't know existed. So while we haven't found one yet, the search continues, driven by the tantalizing possibility that our universe's magnetic asymmetry isn't a quirk, it's a clue. And if monopoles are real, they won't just complete a theory. They'll tear open a new chapter in our understanding of the forces that bind reality together. Neutrinos are the universe's most elusive particles, ghosts that pass through planets like they're not even there. Trillions stream through your body every second, leaving no trace. But here's the puzzle. These tiny particles shouldn't have mass at all, according to the original standard model of physics. And yet, experiments prove they do, just a whisper of it, but enough to defy expectations. Even stranger, neutrinos change identities as they travel, flipping between three types like a cosmic shell game. What if the answer lies not in the neutrinos themselves, but in an invisible field they're dancing with, one we've yet to detect? This is where the neutrino field theory comes in. Imagine neutrinos as swimmers in an ocean, their movements shaped by hidden currents. The water, our hypothetical field, wouldn't just give them mass, it would explain why they oscillate between flavors. Every time a neutrino interacts with this field, it could momentarily stumble, altering its properties in ways that look like spontaneous transformations from our perspective. It's like watching a chameleon shift colors without realizing it's actually reacting to the light around it. The math behind this idea is elegant. Just as the Higgs field slows particles down, giving them mass, a neutrino-specific field could create subtle drag, but with a twist. Instead of a uniform effect, this field might vary in intensity, causing neutrinos to resonate at different frequencies as they travel. Picture a guitar string vibrating at specific notes. The neutrino's oscillations could be harmonics dictated by the field's hidden structure. Some models even suggest this field is linked to dark matter or extra dimensions, making neutrinos accidental messengers from a deeper layer of reality. Clues are already emerging. Experiments like IceCube and Super Kamiok have caught neutrinos mid-oscillation, their energy signatures mismatched in ways that defy simple explanations. Meanwhile, particle colliders hunt for anomalies in neutrino interactions, tiny deviations that could betray the field's influence, the wildest possibility. This field might not be unique to neutrinos. If it permeates everything, other particles could be interacting with it too, just too weakly for us to notice. It's like realizing the air is filled with a scent only certain creatures can smell. What's at stake isn't just a tweak to particle physics. If this field exists, it could rewrite our understanding of mass itself. The Higgs might be the universe's obvious weight giver, but the neutrino field could represent a shadow counterpart, fine-tuning reality in ways we're only beginning to glimpse. And every neutrino that slips undetected through Earth carries with it a secret, a hint that the cosmos is humming with hidden forces, waiting for us to finally tune in. What if time itself could form patterns repeating, stable structures that aren't just passive markers of change but active participants in it? This is the bizarre promise of time crystals, a phase of matter so strange it defies the usual rules of physics. Unlike ordinary crystals, which arrange atoms in repeating spatial patterns like a diamond's lattice, time crystals repeat in time. Picture a snowflake that doesn't just sit there but pulses, cycling through its structure over and over without any energy input. It's as if time itself has a hidden rhythm, and these crystals are dancing to its beat. The key to this phenomenon lies in a concept called temporal symmetry breaking. Normally, the laws of physics don't care about time's direction. They work the same whether you run an experiment forward or backward, but time crystals break this symmetry. Imagine a row of pendulums swinging in perfect sync. Now, suppose every other pendulum suddenly starts swinging at half the speed, locking into a new rhythm that wasn't there before. That spontaneous order, emerging without any push or pull, is what time crystals do in the quantum realm. They're like clocks that wind themselves, ticking indefinitely without friction or decay. The implications are staggering. If time crystals exist, they might be interacting with a hidden temporal field, a backdrop of reality where time isn't just a dimension but a dynamic medium. Think of it like the Higgs field, but instead of granting mass, it could govern how time flows locally. Some theories suggest this field might explain why time seems to move forward at all, or why certain quantum systems appear to remember their past states longer than they should. It's as if time isn't just passing but is textured, with folds and ripples we've never noticed. Experimental proof is already underway. In labs from Harvard to Google Quantum AI, researchers have created primitive time crystals using chains of ions or superconducting qubits. These systems don't just settle into equilibrium like normal matter, they pulse persistently, echoing the hypothetical behavior of a deeper temporal field. Even more intriguing are proposals that cosmic time crystals could exist naturally, structures forged in the extreme conditions of neutron stars or lingering as relics from the early universe. If found, they'd be more than scientific curiosities. They'd be evidence that time itself is a stage with hidden scaffolding, the wildest possibility. Time crystals might blur the line between matter and information. In quantum computing, they're already being tested as error-resistant memory, their stable cycles preserving data better than any static storage. But on a cosmic scale, they could hint that the universe's arrow of time isn't fixed but woven, shaped by underlying fields we've yet to map. It's a reminder that even the most fundamental aspect of our experience, time's relentless march, might be just one note in a far stranger symphony. What if everything we see, the stars, the planets, even ourselves, is just a projection, a cosmic hologram encoded on the edge of the universe? This isn't science fiction. It's the holographic principle, a radical idea suggesting that the three-dimensional reality we experience might be a shadow cast by a hidden information field etched onto a distant two-dimensional surface. Think of it like a movie screen. The images look real, full of depth and motion, but they're actually flat, painted with light. The universe could work the same way, with all the complexity we perceive, every galaxy, every atom, stored as intricate patterns of data on the boundary of space itself. At the heart of this theory lies a profound connection between information and physics. Black holes taught us something bizarre. The maximum entropy, or information, a region of space can hold isn't proportional to its volume as you'd expect, but to its surface area. It's as if the universe is telling us that all the data needed to describe what's inside a box is somehow smeared across its walls. This discovery led physicists like Leonard Susskind and Gerard T. Hooft to propose that the entire cosmos might operate like this, with a hidden information field encoding reality on cosmological horizons. Imagine writing a novel, but instead of filling the pages word by word, you inscribe every chapter's essence on the cover. The holographic principle suggests space-time does exactly that, compressing the universe's entire story onto its outermost surface. But how could a flat surface create the illusion of depth? The answer might lie in quantum entanglement, the eerie link between particles that Einstein famously called spooky action at a distance. Entanglement doesn't just connect particles, it weaves spacetime itself. Some theories suggest that the fabric of reality emerges from vast networks of entangled information, like a 3D image rendered from millions of tiny pixels. In this view, the information field isn't just a passive record, it's an active constructor spinning the threads of entanglement into the tapestry of space and time. Picture a loom where every thread is a quantum bit vibrating with data, and the patterns they form aren't just decorative, they're the very laws of physics. The implications are staggering. If the holographic principle is true, then black holes aren't just cosmic vacuum cleaners, they're ultimate hard drives, storing information in scrambled bits on their event horizons. The Big Bang might not have been the birth of space, but the rendering of it, as the universe's code booted up from a singularity. Even time could be an emergent property, a side effect of how this information field processes change. It's like realizing the movie you've been watching isn't just playing on the screen is writing it in real time. Could we ever test such a mind-bending idea? Surprisingly, yes. Experiments with quantum gravity probes like the holometer at Fermilab hunt for faint pixelation in spacetime, hints that reality has a finite resolution, just like a hologram. Others analyze cosmic microwave background radiation for anomalies that might reveal an underlying information grid. And if we're right, it would mean that every particle, every force, even consciousness itself, is part of an immense data structure, a cosmic algorithm running on the universe's outermost shell. So the next time you gaze at the night sky, consider this. The depth you perceive, the vastness stretching overhead, might be the grandest illusion of all, a holographic mirage crafted by an invisible information field, turning bits into existence itself. Every vacuum in the universe is anything but empty. It's a seething ocean of energy, wild fluctuations that defy even quantum mechanics' strangest rules. This is zero-point energy, the lowest possible energy state of space, where particles flicker in and out of existence too fast to catch. But here's the million-dollar question. Is this just a quirky math trick, or could it be a real, tangible field? One so powerful it might one day propel spacecraft faster than light. The controversy starts with measurement. Quantum theory predicts zero-point energy should be enormous, enough to warp spacetime itself. But when we calculate it, the numbers are absurdly large, suggesting the vacuum energy should have ripped the universe apart long ago. This mismatch, called the cosmological constant problem, makes some physicists dismiss zero-point energy as a mathematical artifact, a placeholder in equations that doesn't correspond to physical reality. It's like balancing your checkbook and finding a trillion-dollar error. You assume you must have typed something wrong, yet others argue the energy is real, just hidden in ways we don't yet grasp. Imagine an iceberg. What we measure is the tiny tip, while the bulk of zero-point energy might be locked in higher dimensions or cancelled out by opposing fields. Some theories suggest it's the engine behind Casimir effect, where two metal plates placed nanometers apart in a vacuum inexplicably pull together. The plates squeeze out certain quantum fluctuations, creating a pressure differential that's been measured in labs. If this isn't just a quantum quirk but evidence of a deeper field, the implications are staggering. Enter warp drives. Sci-fi loves the idea of bending spacetime to zip across galaxies, but physics says it would require negative energy, something that defies classical thermodynamics. Zero-point energy might hold the key. If we could somehow harvest the vacuum's fluctuations, they could theoretically generate the exotic matter needed to stretch spacetime. Picture a surfer riding a wave, except the wave is the fabric of the cosmos itself, and the surfboard is powered by the universe's own restless energy. NASA Eagleworks lab even explored this, testing designs for hypothetical warp bubbles fueled by zero-point fluctuations, but the skeptics push back. Extracting energy from the vacuum, they argue, is like trying to grab smoke. Quantum fields don't behave like batteries. You can't just plug in and drain them. And even if you could, the energy densities required would risk creating black holes or destabilizing space-time. It's the ultimate high-stakes gamble. Tap into the universe's hidden reserves, and you might unlock the stars or unravel reality itself. The debate boils down to a cosmic Rorschach test. Is zero-point energy a ghost in the math, or a dragon sitting atop a hoard of unimaginable power? For now, it's both, a paradox that taunts us with potential, daring us to dig deeper. And whether it's the fuel of tomorrow's starships or just a mirage in the quantum desert, one thing's certain: the vacuum is anything but quiet. It's a symphony of possibility, playing just beneath the threshold of our perception. What if the universe has a memory, a hidden ledger recording every event, every pattern, and every form that's ever existed? This is the bold idea behind morphic fields, a concept that straddles the line between physics and metaphysics, proposing that nature itself might be shaped by an invisible imprint of habit. Think of it like cosmic muscle memory. The more a pattern repeats, the easier it becomes for reality to fall back into it, not because of rigid laws, but because the universe has grown accustomed to certain forms. At its core, the theory challenges one of science's deepest assumptions, that the laws of nature are fixed and unchanging. Instead, morphic fields suggest that these laws might be more like tendencies, reinforced over time by repetition. Picture a flock of birds wheeling through the sky in perfect synchrony. Biology says they're following instinct, but morphic resonance, the mechanism behind these fields, proposes they're also tapping into a collective memory, a pattern solidified by countless flocks before them. It's as if the universe learns, and once a behavior becomes common enough, it crystallizes into a kind of blueprint. The implications are staggering. If morphic fields exist, they could explain everything from why crystals form the same shapes across the cosmos to why animals separated by continents still develop nearly identical instincts. Take termites, for example. When building their towering mounds, they don't follow a central plan, yet somehow their chaotic efforts coalesce into intricate cathedral-like structures. Traditional science credits pheromones and simple rules, but morphic resonance offers another layer: the weight of precedent, invisible threads of influence woven by every termite mound that came before. Skeptics, of course, dismiss this as pseudoscience, a poetic idea without empirical teeth. But proponents point to eerie anomalies. In chemistry, certain complex molecules crystallize more easily today than they did decades ago, as if the process has somehow learned the trick. In biology, rats in separate labs sometimes solve mazes faster when other rats have already mastered them, even with no physical connection. These findings are controversial, but they raise a tantalizing question: could information be transmitted in ways we haven't yet measured? The boldest extensions of this theory venture into cosmic territory. Some speculate that morphic fields might underpin the fine-tuning of physical constants, explaining why the universe's parameters are so improbably perfect for life. If enough universes tried different settings, perhaps the successful configurations left echoes, shaping subsequent realities like grooves worn into a path. It's a wild idea, but not entirely alien to physics after all. Quantum mechanics already shows particles influencing each other instantaneously across vast distances. Could morphic fields be the scaffolding behind such connections, a hidden lattice organizing reality's habits? For now, the theory remains speculative, hovering at the edges of mainstream acceptance. But whether it's ever proven or not, it serves as a humbling reminder. the universe might not just follow rules, it could be writing them as it goes, one repetition at a time. And if that's true, then every action, every pattern, every thought we have might be etching itself into the fabric of reality, shaping what comes next in ways we're only beginning to imagine. Consciousness might be the most profound mystery in the universe, not just how brains create it, but whether it's something far more fundamental, woven into the fabric of reality itself. Some theories push beyond neuroscience, proposing that consciousness isn't just a product of the brain, but a property of the cosmos, mediated by a hidden field that connects everything. Imagine if your thoughts weren't locked inside your skull, but ripples in a vast, invisible medium, like waves in an ocean shared by all minds. This radical idea stems from a puzzle in quantum mechanics. Why does observation seem to collapse quantum probabilities into definite outcomes? The traditional interpretation pins it on measurement devices, but a fringe view suggests it's consciousness itself that does the collapsing. In this model, the universe isn't fully real until a conscious observer interacts with it, a notion that hints at a deeper field bridging mind and matter. Picture reality as a blank canvas and consciousness as the brush that paints it into existence. The implications spiral outward from there. If consciousness is a field, it might explain phenomena like collective intuition or the uncanny synchronicities people report across distances. Studies in telepathy, though controversial, have shown statistically significant results in controlled settings, tiny anomalies that could point to a shared informational layer. Even everyday experiences, like knowing who's calling before checking your phone or dreaming events before they happen, might be glitches in this field's normal operation. Skeptics dismiss these as coincidence or confirmation bias, but the sheer volume of anecdotal evidence keeps the debate alive. Physicists like Roger Penrose have ventured into this territory, suggesting that microtubules in brain cells might harness quantum processes, potentially interfacing with a proto-conscious field. It's a wild leap, but not without precedent. After all, electromagnetic fields were once invisible forces until we learned to measure them. Could consciousness be the next frontier? Technologies like global consciousness projects, which track random number generators for patterns during major world events, hint that mass attention might subtly order randomness, as if human focus nudges the field into coherence. The most tantalizing possibility, if consciousness is fundamental, then the universe might not just contain life, it might seek it, evolving structures that amplify awareness like a feedback loop. From this perspective, stars, planets, and brains aren't accidents but waypoints in a cosmos waking up to itself. It's a poetic vision, one that blurs the line between physics and philosophy, between observer and observed. And whether it's ever proven or not, it challenges us to rethink the very nature of existence, not as a cold, mechanical void, but as a living, thinking tapestry with consciousness threaded through every stitch. What if our reality isn't the base layer of existence, but an elaborate simulation running on a cosmic computer? The simulation hypothesis, once a fringe thought experiment, has gained traction in recent years, not just among philosophers but physicists exploring the eerie possibility that the universe operates like a hyper-advanced video game. But here's the twist: if we're living in a simulation, there must be an underlying architecture making it all work. Enter the simulation field, a hypothetical framework of programmed rules and constraints that could explain why physics behaves the way it does and why reality sometimes feels pixelated. Think of it like the code behind a virtual world. In a video game, gravity, light, and collision mechanics aren't inherent properties, they're scripts executed by the game engine. The simulation field would function similarly, acting as the invisible scaffolding that renders our laws of physics. Particles don't just obey quantum mechanics because it's natural, they follow it because it's the algorithm this field enforces. Even the speed of light might not be a fundamental limit, but a processing cap preventing the system from overloading. It's like realizing the reason you can't run faster in a game isn't your character's ability, but the engine's frame rate. Clues could be hiding in the glitches. Just as software has bugs, a simulated universe might exhibit anomalies, tiny deviations from perfect physics. Some researchers propose hunting for these in the behavior of high-energy particles or the cosmic microwave background. For example, if energy levels in particle collisions always round to neat, discrete values, it might hint at an underlying computational resolution. It's like zooming in on a digital image until you see the pixels, evidence that smooth reality is actually quantized. Others suggest quantum entanglements. Spooky connections could be a feature of optimized coding, reducing the need to render every particle individually. But the real mind bender, this field might not just govern physics, it could explain consciousness itself. If the simulation requires observers to render reality, as some versions of quantum theory suggest, then our awareness could be part of the program's user interface. Imagine waking up one day to realize your thoughts aren't yours alone, but processes running on hardware light years away. Dreams, déjà vu, even hallucinations might not be malfunctions, but background tasks briefly surfacing through the simulation's veil. Skeptics argue this is all untestable metaphysics, but proponents counter with a daring challenge. If we ever develop the tech to create conscious simulations ourselves, the statistical likelihood we're already in one skyrockets. After all, why wouldn't our creators have emerged from their own simulation? The field behind it all would then be the ultimate layer, not a law of nature, but a line of code in an infinite cosmic stack. Whether you buy the idea or not, the simulation field forces a profound question. If reality is programmable, who or what wrote the script, and more chillingly, could it ever be rewritten? Einstein spent the last decades of his life chasing a dream, a single, elegant equation that could tie together all the forces of nature. He called it the unified field theory, a framework where gravity, electromagnetism, and the nuclear forces weren't separate phenomena but different expressions of the same underlying reality. Think of it like discovering that electricity and magnetism, once thought to be entirely distinct, were actually facets of a single electromagnetic force. Einstein believed the universe wouldn't settle for less than unity, that somewhere, hidden in the math, there had to be a grand synthesis waiting to be uncovered. Fast forward to today, and that dream is still alive, though it's taken forms Einstein might not have recognized. String theory, one of the most ambitious contenders, proposes that all particles and forces arise from tiny, vibrating strings, threads of energy so small they'd make an atom look like a galaxy. In this model, the cacophony of the universe's forces is just a symphony of harmonics, with each note corresponding to a different particle or interaction. The catch: these strings don't vibrate in the 3 dimensions we know. They dance in 10 or 11, their hidden movements weaving together gravity and quantum mechanics in ways our everyday math can't yet describe. But string theory isn't the only player in the unification game. Loop quantum gravity takes a radically different approach, suggesting that spacetime itself is stitched together from tiny, indivisible loops, a fabric woven from discrete threads rather than a smooth continuum. Here, gravity emerges naturally from the quantum entanglement of these loops, sidestepping the need for extra dimensions. Picture a quilt up close. You see individual stitches, but step back and it looks like a seamless whole. Loop quantum gravity argues that's how spacetime works. Its apparent smoothness an illusion created by the density of its underlying structure. The irony. These theories, meant to unify, have instead multiplied. Where Einstein hoped for one elegant solution, modern physics offers a landscape of possibilities, each with its own strengths and glaring holes. String theory, for all its beauty, lacks experimental proof. Loop quantum gravity struggles to incorporate other forces beyond gravity. And then there's M-theory, a shadowy cousin of string theory that hints at an even deeper layer where all versions of strings and membranes might converge. It's as if we're trying to solve a jigsaw puzzle where every new piece reveals another missing section, yet the hunt continues, driven by tantalizing clues. The AD-S/CFT correspondence, a breakthrough in theoretical physics, suggests that a universe with gravity could be mathematically equivalent to a universe without it, just a holographic projection of quantum information. If true, it would mean gravity isn't even a force in its own right, but an emergent property of something far more fundamental. Similarly, experiments at the Large Hadron Collider hunt for supersymmetry, a key prediction of many unified theories where every known particle has a heavier twin. Finding even one would revolutionize physics, offering a glimpse of the symmetry underlying all forces. So where does that leave Einstein's dream, in some ways closer than ever? We now know the forces aren't as separate as they seemed. Electromagnetism and the weak nuclear force have already been unified into the electroweak interaction. The pieces are falling into place, even if the full picture remains just out of reach, and perhaps that's the real lesson. The universe might not give up its secrets easily, but every dead end, every near miss, brings us closer to understanding whether its deepest truths are written in strings, loops, or something we haven't even imagined yet. After all, the greatest discoveries often start not with answers, but with the courage to keep asking. Why does time only move forward? Drop an ice cube into warm water and it melts, never the reverse. Scramble an egg and it stays scrambled. The universe seems obsessed with moving from order to disorder, a one-way street we call entropy. But what if this isn't just randomness? What if entropy's relentless climb is guided by something deeper, a hidden temporal field that doesn't just track time but actively steers it? At first glance, entropy feels like a statistical inevitability. There are more ways for things to be messy than neat, so systems naturally drift toward chaos, but dig deeper and puzzles emerge. Why did the universe start in such an improbably ordered state to begin with? And why does quantum mechanics, at its core, treat time symmetrically when our lived experience screams otherwise? The entropic field theory proposes a radical fix. Entropy isn't just happening, it's being imposed by an unseen structure woven into spacetime itself. Think of it like a river's current, invisibly guiding every molecule of water downstream. This field wouldn't just explain time's arrow, it could redefine causality. In Einstein's relativity, time is a dimension where past and future are equally real, just locations on a map. But our perception insists on a flow, a stark difference between before and after. An entropic field might bridge this gap, acting as the universe's stage director. Picture a film reel where every frame exists simultaneously, yet the projector's light, our entropic field, illuminates them in a fixed sequence, creating the illusion of unfolding events. Without it, time might be directionless, a landscape where cause and effect blur into noise. Clues hide at quantum scales. Certain particles, like neutral kaons, exhibit subtle asymmetries in their decay, a tiny preference for one temporal direction over another. These anomalies, dismissed as quirks, could be fingerprints of the entropic field's influence. Even black holes, those infamous entropy factories, might be portals where the field's grip tightens. When matter crosses an event horizon, information isn't destroyed. It's scrambled beyond recovery, entropy's ultimate triumph. Some models suggest this isn't incidental but orchestrated, the field's way of enforcing cosmic order. Here's the kicker: if this field exists, it might not be immutable. Theories of quantum gravity allow for spacetime's structure to fluctuate. In regions where the entropic field weakens, time could stutter or even reverse locally. Imagine a bubble in boiling water where steam condenses back to liquid, a temporary defiance of thermodynamics. Wormholes, if they're real, might exploit these fluctuations, creating shortcuts where the field's rules bend. It's a dizzying thought. The flow of time itself, that most fundamental experience, might be contingent on a hidden variable we've yet to measure. So the next time you watch coffee cool or leaves decay, consider this. What feels like inevitable disorder might be the whisper of something far stranger, a field sculpting chaos into the very shape of time. And if we're right, unraveling its secrets wouldn't just explain why we remember the past but not the future. It would reveal the universe as a place where time doesn't just pass but is pushed. Galaxies aren't just drifting apart in the cosmic expansion, some of them are moving together towards something we can't see. Astronomers call this eerie synchronization the dark flow, a mysterious current sweeping entire clusters of galaxies in the same direction at staggering speeds. Imagine tossing a handful of leaves into a river instead of scattering randomly. They all drift downstream, pulled by an invisible force. That's what's happening on a galactic scale, except there's no visible river, no detectable source of gravity to explain the motion. The leading theory, a hidden field beyond the edge of our observable universe, tugging at matter like a cosmic magnet. This isn't just a minor anomaly. The dark flow spans billions of light years, affecting thousands of galaxy clusters as if they're caught in a current. Measurements from the Planck satellite and X-ray observatories reveal velocities exceeding 600 kilometers per second, far faster than standard cosmology predicts. Normally, the universe's expansion should distribute galaxies evenly, like raisins in rising bread dough. But the dark flow suggests something's pulling those raisins sideways, violating the principle that matter should be distributed uniformly on large scales. It's as if the bread dough is sliding across an unseen table, dragged by a hand we can't see. What could exert such immense gravitational influence from outside our cosmic horizon? One possibility is a remnant of inflation, an exotic field left over from the universe's explosive birth, still active in regions beyond our view. Picture a waterfall where we're trapped in a swirling eddy, oblivious to the vast river feeding it. Another radical idea involves a parent universe, a higher dimensional space where our cosmos floats like a bubble, nudged by gravitational tides from neighboring realities. In this scenario, the dark flow would be the shadow of something colossal brushing past us in dimensions we can't perceive. Skeptics argue it could just be incomplete data or measurement errors, but the signal persists across multiple studies. And if it's real, the implications rewrite our cosmic map. The standard model assumes the universe is isotropic, the same in all directions, but the dark flow hints at a lopsidedness, a preferred direction sculpted by forces from beyond. It's like living in a house where all the windows face one way, unaware there's an ocean on the other side. Some theorists even speculate this field could be linked to dark energy, its influence stretching far beyond the reach of light. The most unsettling possibility, the dark flow might be evidence of a bigger universe, one where our observable cosmos is just a speck in an immeasurably vast structure. If true, the hidden field tugging at galaxies wouldn't just be a curiosity, it'd be a cosmic signpost, pointing toward realms we'll never see but whose gravity we can't escape. And that raises a humbling question: how much of reality's script is written in places we can't even imagine? In the late 1980s, scientists tracking the Pioneer 10 and 11 spacecraft noticed something bizarre. The probes, hurtling toward the edges of our solar system, were slowing down slightly more than physics predicted, as if something unseen was tugging at them from the darkness. At first, researchers dismissed it as a glitch, maybe residual fuel leaking or heat radiating unevenly off the probe's surfaces. But as years passed and the anomaly persisted, a chilling possibility emerged. What if the pioneers weren't experiencing a technical hiccup, but brushing against a hidden force, an unknown field lurking in the void between the planets? This wasn't just a math error, the deceleration was too consistent, too precise. The probes slowed by almost the same tiny amount every year, as if space itself were pushing back against them. Calculations ruled out known forces like gravity from the sun or drag from cosmic dust. Even today, no conventional explanation fully accounts for it. Some theorists proposed a radical fix, a previously undetected scalar field, one that interacts weakly with matter but strongly enough to nudge spacecraft over vast distances. Picture wading through a shallow river. The water barely touches you, but after miles, the accumulated resistance leaves you exhausted. The Pioneer anomaly suggested space might have its own subtle current, an ethereal drag we've never measured. The implications ripple far beyond two lonely probes. If this field exists, it could reshape our understanding of gravity itself. Einstein's general relativity has passed every test thrown at it, except perhaps this one. Modified gravity theories like modified Newtonian dynamics tried to explain the anomaly by tweaking the equations, but they created more problems than they solved. A hidden field, though, that could preserve relativity while adding a new layer to reality, one that doesn't just bend spacetime but permeates it with a faint, persistent influence. Think of it like discovering air resistance after centuries of only accounting for gravity. Even stranger, the effect seems to fade with distance from the Sun. New Horizons, the probe that flew past Pluto, didn't show the same deceleration, as if the field's grip weakens beyond a certain threshold. This pioneer-only behavior deepened the mystery. Was the field tied to the inner solar system, or was it somehow interacting with the Pioneer's unique design? The probe's spin stabilized bodies, their nuclear power sources, even their aluminum shells. Could any of these have acted as unintentional antennas, tuning into a force other spacecraft miss? The most haunting possibility, we might have stumbled onto a cosmic blind spot. Just as dark matter's gravity betrays its presence, the Pioneer's deceleration could be our first whiff of something vast and invisible, a field that only reveals itself at the edges of our perception. Future missions, like those sailing on light-powered solar sails, could finally settle the debate, if they're designed to feel the tug. Until then, the anomaly lingers like a whisper from the dark, daring us to listen closer. After all, if space itself is hiding forces we've never imagined, what else might be out there waiting to rewrite the rules? What if life isn't just a happy accident on Earth, but part of a cosmic blueprint, a hidden force nudging the universe toward biology wherever it can? This is the daring idea behind the life field, a theoretical structure that doesn't just allow life to emerge but actively guides its raw ingredients across galaxies. Think of it like a chef's mise-en-place, where the universe subtly prepares the kitchen before life ever starts cooking. And the most provocative twist: this field might not work alone. Some theories suggest it could partner with panspermia, the concept that life's building blocks hitch rides on comets or asteroids, seeding planets like a celestial farmer scattering seeds. Take amino acids, the Lego bricks of proteins. These molecules shouldn't survive the harsh radiation of space, yet we've found them clinging to meteorites and floating in nebulae. It's as if something's shielding them, ensuring they arrive intact. The life field could be that protector, an invisible scaffold stabilizing organic molecules against cosmic ravines. Picture a river carrying seeds downstream, except the river is the fabric of space itself, and the seeds are nucleotides waiting to bloom into DNA. Even more radical is the notion of directed panspermia, where this field doesn't just passively preserve life's precursors but actively steers them toward habitable worlds. Imagine a cosmic GPS tuning the trajectories of comets to deliver their precious cargo to planets with just the right conditions. Evidence isn't just speculative. The ALMA telescope has spotted complex sugars and alcohols in interstellar clouds, molecules that, under the right field interactions, could assemble into RNA-like chains. Meanwhile, extremophiles on Earth thrive in conditions once thought lethal, proving life's resilience matches the theory's predictions. But here's the kicker: if the life field exists, it might not be unique to our universe. In multiverse models, universes with bio-friendly parameters could be selected by this very mechanism, their physical constants fine-tuned to nurture chemistry that thinks. Critics argue this veers into metaphysics, yet the math holds surprises. Quantum biology hints that enzymes might leverage tunneling effects, as if life exploits deeper field interactions to outperform classical physics. Even photosynthesis, with its near-perfect energy efficiency, behaves like a system attuned to hidden gradients. The boldest vision, this field could be evolutionary, learning which molecular arrangements work best and reinforcing them across galaxies. It's not intelligent design, it's universal trial and error with life as its most successful experiment. So the next time you gaze at the stars, consider this: the cosmos might not just host life. It could be rooting for it. Imagine if the ground beneath your feet wasn't just dirt and rock, but an unstable layer of reality itself. One wrong step, and the entire universe could collapse into a different state, rewriting the laws of physics in an instant. This isn't the plot of a sci-fi nightmare. It's the chilling possibility of vacuum decay, a hidden field lurking in the fabric of space that could, under the right conditions, trigger a cosmic reset button so absolute it would erase existence as we know it. The theory hinges on a terrifying quirk of quantum fields. What we call a vacuum isn't truly empty, it's a seething soup of potential energy, and like a ball balanced precariously on a hill, it might not be in its most stable state. If even a single point in space were to tip over into a lower energy state, say, by a random quantum fluctuation, it would create an expanding bubble of new physics racing outward at the speed of light. Inside that bubble, the fundamental constants we rely on, the strength of gravity, the mass of electrons, even the nature of light, could rearrange instantly. Stars, planets, and life itself would cease to function as they once did, not by destruction but by redefinition. It's not an explosion, it's a rewrite. Here's where the hidden field comes in. This metastable vacuum state isn't just a math problem, it's governed by a real, if invisible, structure sometimes called the vacuum field. Think of it like an invisible membrane stretched taut across the universe, holding everything in its current configuration. Most of the time, it's resilient. But if disturbed, perhaps by a high-energy particle collision or an exotic event in a distant galaxy, that membrane could rupture. The resulting bubble wouldn't just spread through space, it would propagate through time, making the transition inevitable, unstoppable, and utterly unforgiving. There'd be no warning. One moment, reality is as it's always been. The next, it's something else entirely. The eerie part, this isn't pure speculation. The Higgs field, the same one that gives particles mass, is a prime suspect for this kind of instability. Calculations suggest that at extremely high energies, like those in the early universe, the Higgs could exist in a temporary state, like a tower of blocks stacked just carefully enough to stand for now. Particle colliders like the Large Hadron Collider have probed these energies, and so far the tower hasn't toppled. But the deeper we look, the more the math suggests it might not be perfectly balanced. And yet, there's a strange comfort in the sheer scale of this threat. Vacuum decay would be so swift and total that no one would suffer, no one would even realize it was happening. The universe wouldn't end, it would simply become something unrecognizable, its old rules overwritten before any observer could register the change. In a way, it's the most peaceful apocalypse imaginable, a silent transition from one cosmic epoch to another with no witnesses left to tell the tale. For now, the vacuum holds, but every time we push physics to new extremes, every time we probe deeper into the quantum world, we're testing the limits of that stability. And whether the vacuum decay field is real or just a mathematical ghost, it serves as a humbling reminder. The universe might not be as permanent as it seems. The ground beneath us isn't just earth and stone, it's a quantum tightrope, and we're all walking it together. Deep within the neurons of your brain, tiny structures called microtubules might be doing something extraordinary, not just processing thoughts, but tapping into the fabric of the universe itself. This is the wild intersection of quantum physics and consciousness, where a theory called orchestrated objective reduction, or ORCH, suggests that our minds could be quantum computers intertwined with hidden cosmic fields. Imagine if every thought, every flicker of awareness, weren't just electrical signals but quantum vibrations resonating with an invisible field stretching across reality. At the heart of this idea are microtubules, hollow protein filaments that form the skeleton of cells. Traditional neuroscience sees them as mere structural supports, but ORCH proposes they're something far stranger: quantum processors. Unlike classical computers that rely on binary bits, these microtubules could exploit quantum superposition, where particles exist in multiple states at once. Picture a thought forming not as a linear chain of firings, but as a symphony of quantum possibilities collapsing into a single moment of awareness. And here's the kicker: this collapse might not happen in isolation. It could be guided by, or even entangled with, a hidden field that permeates the cosmos, a quantum consciousness field acting as the stage for the mind's performance. The implications ripple outward. If consciousness emerges from quantum processes linked to this field, it could explain phenomena that defy classical biology. Take anesthesia, for example. Certain gases selectively shut down awareness without disrupting underlying brain activity, as if they're targeting the quantum coherence in microtubules rather than just neural firing. Or consider near-death experiences where people report vivid, lucid awareness during clinical death, a state where classical brain activity flatlines but quantum processes might persist, still humming along in the field's embrace. Even more radical is the idea that this field might not be passive. Just as the Higgs field gives particles mass, a quantum consciousness field could actively shape reality through observation. In quantum mechanics, the act of measurement collapses probabilities into definite outcomes, a role traditionally assigned to the observer. But what if the observer isn't just a passive recorder but a participant in the field? Its quantum states influencing the universe as much as the universe influences it. Think of a dance where the dancer and the floor move together, each shaping the other's steps. Skeptics, of course, dismiss this as speculative. Quantum effects are notoriously fragile, easily disrupted by heat and noise conditions that seem incompatible with the warm, wet environment of the brain. Yet discoveries in photosynthesis and bird migration show nature exploits quantum coherence in seemingly hostile conditions. Could the brain, evolution's ultimate achievement, have stumbled onto similar tricks? Experiments are already probing this. Some studies suggest anesthetics alter quantum vibrations in microtubules, while others hunt for telltale quantum signatures in neural activity. The boldest vision: this field might not be confined to human minds. If consciousness is a quantum phenomenon tied to a cosmic field, then awareness could be a spectrum from microbes to galaxies. It's a humbling thought that the spark of self might not be a fluke of biology, but a whisper from the universe itself, echoing through the quantum threads that bind us all. From the fiery depths of Earth's core to the delicate lattices of quartz crystals, our planet might be humming with an invisible harmonic resonance, a hidden crystalline field that shapes everything from tectonic shifts to the rhythms of life itself. This isn't just poetic speculation. Fringe theories propose that Earth's molten outer core, swirling with liquid iron and nickel, generates more than just magnetism. It could be orchestrating a vast geometric energy field, structured like a cosmic crystal lattice, pulsing through the crust and into the biosphere. Think of it like a tuning fork the size of a planet, vibrating at frequencies that subtly influence the world above. The clues lie in strange synchronicities. Certain sacred sites and ancient megaliths, from Stonehenge to the pyramids, are positioned along precise geometric grids, as if aligning with unseen energy lines. Modern researchers call these ley lines, but what if they're surface echoes of a deeper crystalline scaffold? geophysicists have detected ultra-low-frequency vibrations emanating from Earth's interior, known as the Schumann resonances, which mirror the brain's alpha waves. Coincidence or evidence of a field that harmonizes geology and biology? Even more intriguing are piezoelectric crystals like quartz, which generate electric charges under mechanical stress common in Earth's crust and, curiously, also present in the human pineal gland, a structure linked to circadian rhythms and even mystical experiences. Then there's the behavior of tectonic plates. Conventional geology says their movement is driven by mantle convection, but certain anomalies defy easy explanation. The precise fracturing of continental shelves often follows geometric patterns reminiscent of crystal growth, while volcanic activity sometimes aligns in fractal sequences, as if responding to an underlying resonance. Some theorists suggest Earth's core isn't just a chaotic dynamo but a structured oscillator, its rotation and convection currents forging a hidden crystalline matrix that guides seismic shifts. Picture a clockwork mechanism where the gears are made of vibrating iron, ticking in time with the planet's own heartbeat. But the most provocative idea: this field might not just shape rocks, it could whisper to life itself. Studies show that plants grow faster when exposed to specific harmonic frequencies, while migratory animals navigate using Earth's magnetic field with precision that still baffles scientists. Could their internal compasses be tuning into something more nuanced than magnetism, a crystalline lattice acting as a cosmic roadmap? Even human consciousness might be entangled with this grid. Cultures worldwide speak of earth energies and sacred geometries, from the Aboriginal songlines to the Hindu concept of prana. Modern bioenergetics research hints that our cells might exploit quantum coherence, resonating with environmental frequencies in ways we're only beginning to grasp. Skeptics dismiss this as New Age fantasy, but the science of crystallography offers tantalizing parallels. Crystals store information in their atomic arrangements, and some superconductors exhibit fractal patterning eerily similar to fault lines or river deltas. If Earth's core hosts even a fraction of this order, its field could be far more than a geological curiosity. It might be a silent architect weaving the physical and the living into a single, resonant tapestry. The question isn't just whether Earth hums with hidden geometry. It's whether we've been dancing to its rhythm all along, mistaking the pulse of something vast and ancient for the random noise of an indifferent world. And if we're right, the planet beneath our feet isn't just our home, it's a living crystal singing a song we're only now learning to hear. What if human thought could ripple through the fabric of reality itself, bending matter and probability with nothing but focused intention? This is the radical proposition of the noetic field, an invisible medium said to connect all minds, where collective consciousness doesn't just observe reality but actively molds it. Unlike traditional fields in physics, this one isn't governed by equations or measurable forces. It's a bridge between mind and matter, a cosmic canvas where thoughts might leave brushstrokes. The concept emerges from centuries of esoteric traditions, but modern noetic science, pioneered by institutions like the Institute of Noetic Sciences, seeks empirical footing. Take the infamous Global Consciousness Project, a network of random number generators placed worldwide that, during globally significant events like 9/11 or the Olympics, produce statistically improbable patterns. It's as if the machines feel the collective emotional surge, their outputs briefly synchronizing in ways chance can't explain. Skeptics dismiss it as data noise, but proponents see a fingerprint evidence that human focus might nudge randomness into order through an unseen field. Then there's the Princeton Pear Lab experiments, where participants attempted to influence mechanical systems with their minds. Over decades, results showed slight but persistent deviations from statistical norms, dice landing on sixes more often when willed, or pendulums swinging counter to physics when concentrated upon. The effects were tiny, but their consistency hinted at something profound. Intention might interact with the noetic field like a weak force, subtle but measurable. Imagine throwing a stone into a pond and watching the ripples, except the pond is reality and the stone is a thought, but the wildest implications lie in healing. Studies on distant prayer and intention, like those examining patients whose names were unknowingly given to remote groups to send healing, sometimes show accelerated recovery rates compared to controls. In one striking case, a sealed Petri dish of bacteria grew faster or slower depending on meditators' focused intentions miles away. If reproducible, this would suggest the notic field doesn't just respond to consciousness but carries its imprint across space, a carrier wave for mind's influence on matter. Critics argue these phenomena could stem from confirmation bias or undetected variables, and they're right to demand rigor. Yet the notic hypothesis offers a framework unifying anomalies from placebo effects to quantum observer effects. Perhaps the field operates like a cosmic Wi-Fi. It signals strongest when minds resonate in unison. During mass meditations or global crises, when millions share a single emotional frequency, the effect might amplify, warping probability at scales we can barely fathom. The ultimate question isn't just whether this field exists, but what it reveals about reality's nature. If mind and matter are truly entangled through the notic field, then consciousness isn't a passive byproduct of the brain, it's a cosmic participant, shaping the universe even as the universe shapes it. And that raises a thrilling possibility. The greatest force in existence might not be gravity or electromagnetism, but the collective whisper of every thinking mind humming in the dark. Mainstream cosmology paints the universe as a place ruled by gravity, dark matter sculpting galaxies into being, dark energy pushing them apart. But what if we're missing half the story? Enter plasma cosmology, a radical alternative where electromagnetism isn't just a background player but the prime architect of the cosmos. Imagine a universe not of isolated islands drifting in the void, but of crackling electric currents weaving galaxies together like beads on a string. This is the plasma universe theory, and it turns everything we think we know about cosmic structure on its head. At the heart of this idea is plasma itself, the fourth state of matter, where atoms are stripped apart into a sea of charged particles. Over 99% of the visible universe exists in this electrified state, from the heart of stars to the vast interstellar medium. Plasma cosmologists argue that when you have this much charged material moving at cosmic scales, electromagnetic forces can't be ignored. Picture a thunderstorm the size of a galaxy, with lightning bolts stretching millions of light years, their currents shaping the birth and death of stars. While mainstream models treat these forces as negligible at large distances, plasma physics suggests they might be the hidden hand behind the universe's grand design. Take galaxy formation. The standard model relies on dark matter's gravity to clump gas into spinning disks, but plasma theory offers a different script. Swirling electromagnetic fields could generate colossal pinches and whirlpools in interstellar plasma, naturally funneling matter into spiral arms without any dark matter required. Experiments in labs even mimic this effect. When high-energy plasma is subjected to strong currents, it self-organizes into eerily galaxy-like structures, complete with rotating cores and filamentary arms. It's as if nature has been showing us the answer all along, hidden in the behavior of electrified gas. Then there's the cosmic web, the sprawling network of galaxy clusters and voids that looks like froth on an ocean. Mainstream cosmology credits dark matter's gravity for this lacework, but plasma proponents point to something more tangible: Birkeland currents. These are vast, twisting channels of electric current that flow through space, named after their discoverer, Christian Birkeland, who first proposed in the early 1900s that auroras were powered by solar currents. At cosmic scales, these currents could form colossal filaments, energizing plasma into glowing strands that outline the web's structure. Telescopes have even spotted hints of this: thin, magnetized threads connecting galaxy clusters, glowing with synchrotron radiation just as Birkeland's models predicted. But the boldest claim, plasma cosmology, might render dark energy obsolete. Instead of a mysterious force accelerating expansion, the universe's large-scale motions could be driven by electromagnetic interactions between galactic circuits. Imagine galaxies as nodes in a cosmic power grid, their movements dictated not by invisible energy but by the push and pull of billion-year-old currents. Even the redshift of distant galaxies, the key evidence for expansion, might have an alternative explanation. Some plasma models suggest light could lose energy as it traverses magnetized plasma over cosmic distances, mimicking the effect of an expanding universe without the need for dark energy. Of course, the plasma universe isn't without controversy. Critics argue that while electromagnetism dominates small-scale phenomena like solar flares, it's too weak to overcome gravity's grip across millions of light years. Yet plasma cosmologists counter that we've barely begun mapping magnetic fields at intergalactic scales. Recent discoveries of coherent magnetic fields spanning galaxy clusters suggest their influence might be vastly underestimated. It's like realizing the ocean isn't just water but a network of hidden tides guiding everything beneath the surface. Whether plasma cosmology ultimately overturns mainstream theories or merely complements them, it forces a vital question. Have we been so fixated on gravity's role that we've blinded ourselves to the universe's electric heartbeat? The cosmos isn't just a dark, silent void, it's a living circuit, crackling with currents we're only beginning to trace. And if we're right, the night sky isn't just a scattering of stars, it's a neon sign written in the language of plasma, waiting for us to decipher its glow. Black holes have long been the ultimate cosmic paradox, regions where gravity is so intense that not even light can escape, swallowing everything that crosses their event horizons without a trace. But in the 1970s, Stephen Hawking made a startling discovery. Black holes aren't completely black. They slowly leak energy, emitting what we now call Hawking radiation, a faint glow that eventually causes them to evaporate entirely. This revelation opened up a terrifying question. If a black hole vanishes, what happens to all the information about the stars, planets, and atoms it consumed? According to quantum mechanics, information can't be destroyed, yet Hawking's math suggested it was disappearing forever. This contradiction became known as the black hole information paradox, a puzzle so deep it threatened to unravel our understanding of physics itself. Enter the black hole information field, a radical solution proposing that the universe has a built-in backup system, a hidden structure that preserves information even as black holes appear to erase it. Think of it like a cosmic hard drive, silently recording every bit of data that falls into a black hole, then encoding it into the Hawking radiation that eventually escapes. The key lies in the holographic principle, which suggests that all the information within a black hole's volume is actually stored on its two-dimensional event horizon, like a quantum fingerprint. As the black hole emits radiation, this field ensures the information isn't lost but subtly imprinted onto the outgoing particles. It's as if the universe is running a cosmic encryption program, scrambling data in a way that seems random but can, in theory, be decoded. The implications are staggering. If this field exists, it would mean that black holes aren't the ultimate shredders we once feared. They're more like cosmic librarians, meticulously cataloging everything they consume before returning it to the universe in a transformed state. Some theories even suggest that the information field might be entangled with the fabric of spacetime itself, creating a feedback loop where the act of information preservation shapes the very geometry of the black hole. Picture a swirling vortex where every atom that falls in leaves a ripple on the surface, a kind of quantum braille that tells the story of its origins. But how could we ever test such an abstract idea? Surprisingly, physicists are already working on it. Advanced gravitational wave detectors could one day pick up subtle distortions in the echoes of black hole mergers, hints that information isn't vanishing but being subtly redistributed. Meanwhile, quantum computers are being used to simulate black hole dynamics. searching for telltale patterns in how information scrambles and reemerges. Even Hawking himself eventually revised his stance, suggesting that black holes might not destroy information after all. They might just hide it in ways we don't yet understand. The most profound takeaway: if the black hole information field is real, it would mean that the universe operates like an unimaginably complex computer, where nothing is ever truly deleted, just rewritten. Every star, every planet, every conscious thought that falls into a black hole might still exist, preserved in a hidden layer of reality we're only beginning to decode. And that raises a humbling possibility. The universe might not just have memory, it might have a soul. From quantum whispers to cosmic holograms, these 30 theories reveal a universe far stranger than we ever imagined, a reality woven from hidden fields we're only beginning to trace. Think about it. The Higgs field gives particles mass, dark energy's phantom push accelerates galaxies apart, and actions might be the invisible architects of dark matter. Time crystals could rewrite our understanding of entropy, while the holographic principle suggests everything we see is just a projection from the edge of space-time. And let's not forget the terrifying elegance of vacuum decay, a cosmic reset button lurking in the quantum shadows. Each of these ideas isn't just science fiction, they're serious frameworks that could shatter and rebuild physics as we know it. What's truly astonishing is how interconnected these theories are. The same fields that might explain galaxy-spanning dark flow could also hold the key to quantum consciousness, linking the vast and the infinitesimal in a dance we're just starting to map. The universe isn't just governed by the forces we've named, it's humming with unseen players, each tuning reality in ways that defy intuition. Maybe the inflaton field birthed the cosmos, or perhaps we're floating on a brain in a higher dimensional bulk, nudged by forces from neighboring universes. The deeper we dig, the clearer it becomes. The laws we once thought absolute might just be local ordinances in a much grander scheme. So here's the million-dollar question: which of these theories speaks to you? Does the elegance of supersymmetry's gravitinos spark your curiosity? Or does the haunting possibility of a simulated universe send shivers down your spine? Maybe you're drawn to the poetic symmetry of morphic fields, where the universe itself might be learning as it goes. Whatever resonates, one thing's certain: we're standing at the edge of a revolution. Every anomaly in particle colliders, every unexplained twist in galaxy rotations, every flicker of quantum weirdness is a breadcrumb leading us toward something profound. The conversation doesn't end here. Dive into the comments and tell us which hidden field theory feels most alive to you. Is there one we didn't cover that keeps you up at night? Science thrives when we wrestle with the unknown together, and who knows? The next big breakthrough might start with a spark from someone just like you, staring at the stars and wondering what else is out there whispering in the dark.